Good afternoon, everyone. So you can hear me, right? My voice is little bit trying to speak up. I'm speaking about some optimal transportation of movement. I first describe what the problem is, and I'm going to tell you what I'm going to do in this symposium. So in this symposium, we're taking 4 classes. Okay, and so I hope that you haven't seen this topic before, or maybe giving some background. So the first 2 lectures will be on the those 2 backgrounds. Yeah.
So a little bit louder.
Okay. Okay.
The mic will be good.
Yes, sir. So is there a no mic?
Mic is not going to sync.
Okay. All right. So the first 2 lectures will be the background on this problem, and the next 2 lectures will be on after this results. And so let me first describe the problem, and then I will tell you what I'm going to do. So the problem is as follows. Suppose you have an amount of soil and you want to extract from the ground, and you want to incorporate the soil in a construction one. Okay, so you are going to extract soil from here, and you are going to transport it here and build this one. Okay? So your the soil location, this one, and what you are going to build is already known to you. You already know. Okay? So the only thing you don't know is that the allocation. Okay? Which, suppose this is a point X, and you want to transport the mass and make it useful at a construction site Y, and this allocation, okay, this assignment you have to determine. Okay, so I'll explain in a bit more. So this is modeled by a probability measure. Okay, so the amount of soil will model this by a probability measure. I hope that you know what is a probability measure, and in this context, I will be taking a set of all Borel probability. Okay. So the soil is modeled by a probability measure, and also you don't want to extract excess amount of soil, right? And construction site is also modeled by probability measure. So basically, mu of A, so you choose a location A, a subset of Rn, and mu of A basically tells you and how much soil located right? And similarly, mu of B, amount of soil that can be transported to B. Okay? So this is what we mean by we model the amount of soil and the construction site by probability measure. Okay? And the transportation is not free, right? So it's cost. So if you want to transport an amount of mass from X to location Y, so it will cost something. So that I will denote by CX1. So this cost will be modeled by measurable map from Rn to 0 infinity. Okay, so I'm assuming the cost is non-negative, which is decent assumption, and here I'm including infinity, which tells you that some locations may be forbidden. Okay, it might be, I mean, too much. It's too expensive to move. Yeah. Okay, so plus infinity is allowed, and this is measurable cost transfer. Okay. What do I mean by transport? So I have to tell you what is the transport means. Okay, so according to my model, okay, so if you choose a set B here, okay, and suppose you have made some construction on that set B, and then the soil you extracted must come from somewhere from here, from where you extracted, right? So this is modeled by a Borel map T. This is the model of how we assign mass, how we transport mass. So basically, if you choose a point P, choose a set P, and you are looking at the mass located at B. Okay, so that mass must come from some of the extraction site, right? And this extraction site is P inverse of B. And you are incorporating all the mass which you extracted from there to this construction site. So this is a descent analysis. And this is true. This should be true for all Borel maps, all Borel subset of R. So have you seen this kind of identity before? Well, if you haven't seen, okay, so this is what we call push forward of a base. Okay, so I will, if such a identity holds for all B, then we'll call mu is the push forward of mu under this map. This is my notice. Okay? And by monotone convergence theorem, so this is equivalent to saying that for all integrated functions, if you integrate with respect to the measure d nu, and g is integrable with respect to the measure d nu, then this is equivalent to integrating g composed p with respect to measure d nu. Okay, so these are all equivalent. So now let us look at what is the cost. Okay, so basically, so this is modeled by email. Okay, so you are transporting from x to the point tx, and the amount of mass located here is infinitesimal amount dx. Right? So this is the mass located, you can say, around the point x, and that is the cost of moving mass x to tx, right? And therefore the total cost is, you have to integrate over all such points, right? So this is the total cost. And of course, the problem is to minimize this total cost. So the problem is to minimize the total cost, and here you see everything is known except for this map T. Okay, so you have to find, you have to minimize over such transport map T, which is forward mu is equal to mu. Okay. So this is our problem, and this is the Monge problem. Okay, so the origin of this problem is back in 1781. Can you believe that? I mean, this long back, Monge considered this problem, but his cost was only distance cost. Okay, so he considered Chy is mod x minus y, and so this problem is solved only recently. I mean, started to solve around 1977 to maybe 2000. Around this period, I mean, the problems solved for many different cost functions that I will mention later. So you see the gap, almost 200 years to solve this problem. Okay, so in this talk, what I'm going to describe, the first two lectures will be to describe this problem in more detail. Here I will mention a result due to Vernier, which Vernier first proved the existence of such optimal map for quadratic form. And then Caffarelli and Caffarelli did it for strictly convex cost. Okay, so let me just write x minus y whole part. Okay? And Tang Mo Macan. So So all these results only concentrate on strictly convex forms. And but I'm not going to touch the case p equals to 1, that you will see why. And I'll just put a start that I will not cover this topic, where Caffarelli also contributed with his co-authors Lacan and Tillman. Around 2001, so they proved existence of Monge problem for this kind of cost, where this is a norm in Rn and which is strictly convex. I mean that if you consider the ball is strictly convex. Okay, so I'm not going to touch this result. Rather, I will concentrate only on this kind of quadratic cost. And the third lecture will be about the geometry or the regularity of such math. So formally, if you look at this constraint, let us do some formal computations. Okay, let me assume for the moment your mu is given by a density in Ps, and mu is also given by a density dy. Then let us look at this constraint gr. So here I should write some other notation. Perhaps let me use s height. Okay, I want to keep f and g for the densities. Okay, so basically, psi y gy is equals to log 2x fx dx, and if I do the change of variable y equals to dx, then this will become psi of dx gy, and then Jacobian of t will come equals to psi of, which is equals to this identity, and this should hold for all test functions c. So this quantity will be equal to this one. So therefore gy within gx equals to, sorry, here dx. So this is the equation. This is the constraint used. Okay. So a particular case which will appear when we consider quadratic cost is when t is given by the gradient of a convex function. Okay, so assume that gradient of a convex function, then you know that so this will become d2. Now phi is convex, so this has a sign, so we can determine it is non-negative. So we can just remove the modular and you get and this is for the Monge and Kantorovich equation that Avneet will discuss in more detail. But however, let me just tell you this fact that so Avneet will discuss the regularity of such solutions. But I mean, of course, you have to be careful what we mean by a solution. Like he is only convex, and you have seen several process of solutions over the last, I mean, yesterday, and viscosity solution, weak solution. So, and this is not a, I mean, you have to be careful what do I mean by solution. Okay, so what the regularity theory that Avneet will discuss, will be talking about Alexandrov solution. I will define what we mean by Alexandrov solution much later, but the solution what we got will wait here will be much weaker than that. Our third lecture will be concentrating on the so here the solution will get. Okay, so of course you see if the existence of an optimal map, and if the map is given by a gradient of a convex function, so we solve this kind of equation, right? So the meaning here, the solution meaning what is, this is the formal derivation which we got from the push forward identity, right? So this is only we have. That is the only thing we know, right? So this is of course a notion of solution that we will call because it is quadratic, and Brenier was the first one who proved the existence of such map. We will call the Brenier solution. So in general, Brenier solution is weaker than the Alexandrov solution, but under certain assumptions, they are equivalent. And that is the third lecture that I will concentrate on. Brenier solution is equals to Alexandrov solution. And finally, the fourth lecture again will be concentrating on another useful method, Caffarelli, again concentrating on such quadratic cost, and that is called. So the result is something like, suppose your measure mu is Gaussian, square root 2 dx, and your target measure mu is more concave than this one, in the sense that this is minus w minus mod x squared by 2 y dy. Okay? So your, and here w is convex, and t is the optimal map. Corresponding to the cost function mod x minus y squared. Caffarelli showed that such maps are complex. That is dx minus dy is equals to mod x minus y, and this is known as Caffarelli's contraction theorem, and that will be the content of our fourth. So I hope that it is clear what we are going to see in this four lectures. Okay, so let now let us now discuss further what is the difficulty in this Monge problem, why it was open for nearly 200 years. Okay. All right, so difficulty. So if you are seeing this topic for the first time, the first question you would ask, well, I mean, forget about optimal one. Is there a one such map? Okay, I mean, of course, that's genuine question. Okay, so in general, there may not be any given any arbitrary measure mu nu. There may not be even a map. Okay, for example, the easy one is the Dirac mass. Okay, so suppose mu is the Dirac mass located at any point, okay? And T is any map, any foreign map. If you compute the push forward, you will find that it is just Dirac mass located at x naught. Okay, so T at Tx naught. So basically, the push forward of the Dirac mass is Dirac mass. So if your target measure is other than the Dirac mass, you don't have any T, and therefore the set of all such constants is empty. Okay? But under some assumptions on mu and nu, there are one can construct such maps, and that is known as couplings in probabilities. Okay? And I'll just mention a few names where you can build such map. Okay? So one such example is the north map. These are not the particular optimal maps, but some way of transporting maps. And another one which uses the PD method, that is Monge and Kantorovich. So if your measures are absolutely continuous, then one can use these two techniques to find one such map. Okay? So I'm not going to. So the bottom line is, if your mu nu are sufficiently regular, then the set of all constants is non-empty, so that this doesn't become void and your infimum becomes infinity. Okay? All right. Okay, so that is the easiest difficulty to handle. The second difficulty is that, well, there might be a map, but may not be any optimal one. Second difficulty is that there exists a transport map. That means the T we are denoting, but no optimal one. So here is an example. So you consider R2 and you just consider the line y equals to 0, okay? And so this is where your mass is located uniform. Okay, so your mu is just the H1 is restricted to this line. So this is the line 0, 1 cross y 0. Okay, so and you want to transport all the mass which is uniformly distributed in here to the places which is left to this one and right to this one and same distance. Okay, so say this is -1 and this is 1, in terms of y coordinates. So your mu is half of the mass distributed, uniformly here, and half of the mass distributed uniformly. 1 cross -1 plus 1 restricted to cross. Yeah, of course, I mean, so if you use your intuition, then the best possible, and say that the cost is say mod is -5 also. So it looks like from the picture, I mean, it is better to send all the mass from here to here. I mean, straight line minimizes the distance, right? So if you just here the half, I mean, uniformly distributed along the half, right? So if you if you just break the mass into half and distribute along this line, this would be the optimal cost, right? So that is what you should expect, and indeed that is true. And so optimal cost is fine, but here is an example of how to build a map which approximates the total cost. Okay, so you can divide this by uniform distances, say of length, say for k. So you divide this into 2k, and here you divide into 2k. Here you also divide k, and here you divide into k uniformly. This distance are 1/2k, and the first one you send to here, the second one you send to here. So is this map a little bit clear? This picture is not clear. Right? So let me just draw a few lines. Okay. This one, this one, this one.
What is H1?
H1, the host of method. Yes. So
The second one is new.
new. This one is the target method. So the transport map you want to construct is something like, so here you divide it into 2k steps, right? And here into k steps. So these steps looks little bit twice the size of this one, right? So you transport this mass to here, and this mass to here, and this mass to here, and so on. Okay, so this is how you can at least, I mean, you distribute all the masses to here, here, and all the masses which is located at here, and this way you can construct a map which for each k you can construct such a map which approximates the optimal cost. So of course this is not a rigorous one, but at least from the picture it looks like that it is quite possible. And if you believe me or not, that this map actually approximates the total cost. But you can easily show that such a map, optimal one cannot exist. So the intuition is that, I mean, if you do not break the mass, then it will increase your cost, because you have to go a little bit you cannot go straight, right? So if you send all the mass from here to here, then this mass has to go somewhere which is not exactly a straight line, and therefore you have to forward a little bit more.
What is the optimal cost?
1 actually. In this case, it is 1. So here I forgot. So the distance is mod x minus y. So the here the distance is 1. So this is 1. Okay. All right. So this is again tells you that you need certain regularity on the meter to be able to talk about optimal max. Okay. All right. The third difficulty is again this Jacobian equation. Okay. So this constraint, as you can see, is very highly nonlinear.
It doesn't sync well with the recording. It is not.
So is it audible? I mean, this voice, is it?
It is perfectly audible.
Okay, okay, okay. Okay, okay.
Do these T's have a weak limit?
Sorry?
Do these T's have weak limit at k goes to infinity? These transformations?
Of course, I mean, I see. So, what did it cost? So you have a bound on the cost. So basically, you have L2 bound on the T, right?
So what I'm saying is that total cost is 1.
Yeah.
What I'm saying is that these TKs, let's call this TKs. What does the TK look like at k goes to infinity?
So it will, I mean, it will converge to actually your,
Some kind of Cantor function?
no.
Sort of like Rademacher sort of basis, right? 1 minus 1. Arbitrarily close.
Right.
Rademacher
Yeah.
type, yeah.
Of course, it will have a weak limit. Always have to. Okay. All right. And again, I mean, thanks for pointing out that. So that is the main, I mean, problem. You see here, the problem is that TK, if you take a minimizing sequence, TK, which approximates your minimal cost, and from this example, you see that TK always have a LP bound, right? TK have LP bound. I mean, LP, I mean, very vaguely I'm saying because it depends on the cost. If your cost is like mod x minus y power p, then TK have LP bounds. Okay? But you see the constant, this constant is very highly nonlinear, and you cannot pass to the limit in this constant. Even if TK converges to some t in quickly in LP, then this constant is not preserved. Okay? So there are examples. So basically, the third difficulty is the constant is not closed. But fixed. Therefore, the standard direct method in calculus of variations it's doesn't apply here. Right? You cannot go any. Right? You take a minimizing sequence and try to prove the convergence, but it doesn't work in this case. Yeah? You cannot even prove that the constant is bigger. Okay? All right. So these are the main 3 difficulties, and it was quite unreachable for some time. So the first major breakthrough in this direction came around 1940s. Okay? So, around 1940s, Kantorovich, so he was also studying some kind of transport problem, and he was not aware of Monge's this problem. And so the only difference is on this problem, Kantorovich problem and the Monge problem is that the way of transportation is different. Way of so here Monge considered transport map and he considered transport plan. So what do I mean by transport plan? So pi will be called a transport plan if it is a joint coordinate measure on Rn cross Rn and has marginals, first marginal mu and second marginal mu. A pi of Rn cross B is equal to mu. So this is what we mean by a transport plan. Okay, so it's a joint coordinate on Rn and which has first marginal mu and second marginal mu. And equivalently, you can write these two constants phi x plus psi y equals to integral mu x psi y all phi psi which are integrated. He considered this kind of transportation plans, and we will denote all such plans by capital Pi, pi mu. And according to our definition of this push forward, this constant can be written as, so let P I be the projection onto the ith band. So P1 denotes the projection onto the first factor, P2 denotes the second factor. Okay. So this constant together I can write as pi measure on Rn cross Rn. This first projection push forward pi is equals to mu and P2 push forward pi is equals to mu. Just another way of writing this constant. Okay, nothing serious. Okay, and Kantorovich wanted to minimize again the total cost, it's 1 d pi x. Okay, so now it is one integral over Rn cross Rn. Okay. And he wanted to minimize over all such transport plans. So that I will denote by K. Okay. All right. Okay, so I hope the problems are clear. Okay. Now here this has several advantages. The first advantage is that this set is never empty. Capital Pi never empty. The product measure always there. The product measure is always there. So this set is never empty. And if you assume that say C is bounded, then infinity is finite. So that is good. The second is that, see, this is a linear optimization. So it is linear, you are minimizing on over pi, and with respect to pi, this is just a linear. So basically, pi going to pi is linear, and therefore these are stable under weak limits. And thirdly, this set capital Pi mu, this set I'm going to tell you prove in a moment that this set is actually a convex. Convex is here, right? And actually is convex. So therefore, if you assume, under very mild assumption, if C is, let's say, continuous, then KB always admits a solution. So the convexity is clear. The compactness, I don't know whether you know about Prokhorov's theorem. Probably. Okay. So let me just mention that theorem. So, what about weak convergence of measures? Anything? No. All right. So let me just mention a few lines about weak convergence of measures. So phi k is said to converge weakly to phi if all continuous bounded functions Ck converge to integral p d phi. This is for all continuous bounded. And you see, you know Banakala-Gulu theorem, right? So basically, this is the weak star convergence. Okay? So if you consider the continuous functions over a compact set K, and if you consider the dual, so these are set of all random measures on RA. And therefore, the weak star convergence will be against continuous bounded functions, right? So basically, CK to 1, right? So this is why you talk about weak star convergence, and therefore the action against the CK space, right? So X star, weak star convergence is here, right? And the weak star convergence is just the action with respect to X. Right? This is what we are talking about, right? So this is in the dual, this is the element, CK. And this is basically one other. So if you assume, so here I am assuming K is compact. Okay, so if it is not compact, for example, in case of RE, then you have to talk about, you have to assume the decay at infinity. Okay? And here I am considering on the probability measure, so which can be improved to continuous bound. Okay, so this is what I mean. Okay, so the reason is that as soon as you have this kind of convergence, so that will automatically tell you that if these are probability measure, this is also probability measure. So, all right. Okay, so and the Prokhorov's theorem tells you that if a sequence of measures is tight, phi k is tight, then it is free compact. Okay? Then up to the subsequent phi k converge to weakly some phi. And by tight, I mean that you must have a control at infinity, and it is tightness, meaning that for every epsilon positive, there exists a compact set K such that outside this K, phi K has only small amount of mass. And this is equal. One way is clear, so other implication is also true. Okay? So if this convergence holds, and for a single measure, you see if you consider a complement of the compact set, if compact set is sufficiently large enough, then this is small, right? And therefore these are uniformly small. Okay? So basically, convergence implies this one is okay, but the other is also okay. And I'm going to show that this set is actually tight. Okay? So, which is easier way to show the compactness of this set. All right. Okay. So as I mentioned that okay, so this set phi here is compact. So all we have to show, you have to prove the tightness of this measure, right? So let us take mu are fixed. Okay? Even any epsilon positive, so you choose compact sets K and L are fixed, right? So K complement has very small mass, mu L complement has small mass, and then we just consider K cross L. Okay, so this is again a compact. Okay, so if you take the complement is included in K cross K complement for Rn union L complement Rn cross L complement. And if you consider some pi measure, then this one, the first one gives you mu of K complement plus second one gives you mu of N complement, which is very small. Okay, so basically for each pi, this holds, and therefore the tightness holds, and therefore it is compact. Okay, so the second ingredient is about this one. Okay, of course, as soon as it is compact, if you consider C continuous bounded, this becomes just continuous with respect to the V star convergence, and therefore the sequence admits a solution. Okay? But more generally, what you can prove is that pi is very wide assumption. So I'm assuming C is non-negative. So if I assume that only one semi-continuous, of course, as I mentioned that if it is continuous, then this integral is continuous, right? And if it is not semi-continuous, this is actually not semi-continuous, and you are only minimizing, right? So this is enough to ensure that Kp admits a solution. So the compactness of pi and the lower semi-continuity of this functional ensures Kp after each problem always admits a solution. Of course, I'm assuming that the total cost is finite. All right. Okay, so you see, the relaxation of Kantorovich is much more, simpler than the original Monge problem. Right? But of course, how does these problems are related? Okay. So suppose your pi. Okay. So you see the constraint. One constraint is. Let us assume the Monge problem. Okay. So suppose T is a and push forward mu to mu. Okay. Then you consider pi, which is just identity and T push forward mu. Then you can directly compute that integral C y pi x y. Okay. Now you see pi is just the identity push forward T, right? So when I want to write with respect to mu, right? So this is the push forward d mu x. So I have to compose C with this map T, right? So C compose this identity T is C of the first component is identity x, the second one is T, right? So Tx. So basically, your Kantorovich problem is equals to the Kantorovich total cost is equals to the Monge total cost for this part. So given a T, we can construct a pi, right? So given a plan, we can construct given a map, we can construct a plan, and the cost is equal. So, and we are minimizing. So Kp Kantorovich problem is always lesser equal to original Monge problem. Okay. The converse is in general not true. The equality in general doesn't hold. Okay, so under such assumption. But for the moment, assume that. So I know that an optimal pi exists. Okay, so there exists an optimal pi for K, which we proved always exists. Okay. Suppose this pi, if this pi is concentrated on a graph. What do I mean by that? What do I mean by that? Yes, there exists gamma subset of Rn cross Rn that phi of gamma is equals to 1 and this gamma is a graph. That means if 2 points xy and xy prime with the same same first component equal, then this implies y equals to y prime. Okay? So if you have if your phi is concentrated on a graph, then from this definition you can easily see that you can afford for each x you can uniquely define a map. Okay? So t x equals to y, the unique y for which xy in gamma, and this t is gives you the dashed map. So you obtain a pi and assume for the moment that this pi is concentrated on a graph, then actually your pi is given by a map. Right? So basically, all your solution to Monge problem is boils down to showing that the optimal pi is concentrated on the graph. Okay. So still, I mean, that is still a serious problem. I mean, showing that it is concentrated on a graph is not a trivial job. Okay. So the second missing piece for the Monge problem again came from the Kantorovich. Okay, so through his duality. Okay, so see, Kantorovich he was, this problem he was studying around 1940, and he was basically economist. Okay, and he received Nobel Prize for works in economics. Okay, and that is the time when the linear programming was basically originated. He is one of the founders alongside Stanley. So he was interested in linear programming problems. And the Kantorovich problem, as I mentioned, that it is a linear problem for a convex cost. So basically, an infinite tensor linear programming problem. And Kantorovich, by that time, he somehow mastered, how to deal with it. Okay? So duality is one of the techniques. So if you know a little bit of convex analysis, so you'll see that the duality comes naturally. But let's not get into that. Okay, I'll just motivate from a different point of view. Okay? So basically, Kantorovich, so this is the Kantorovich problem. He reformulated this problem in this way. Okay? So suppose Kantorovich duality. So let us now again come back to our original problem. So earlier we were extracting soil and just constructing building. Okay, so let us reformulate this problem in the following way. Suppose you have bakeries at different places of the cities, bakeries, and you have cafes at different places in the cities. And you want to transport breaks from these bakeries to cafes. Okay. Of course, so here now in our model, mu is model the bakeries. Okay. The breads, total number of breads in bakery. That means if I give mu of A, basically this is the number of bread located at the location, number of bread in a bakery located at A. And mu of P is basically the number of bread required at cafe located at B. Okay? And each morning you would transport your breads to bakeries. Okay? So, and even in a large city, there are a lot of bakeries and a lot of cafes. And you want to transport bread, and of course, the number of breads which is produced at each bakery and number of cafes which is required. I mean, it's all known, right? So you have some statistics, you know how much bread you need. Here you know how much bread you can. And for the sake of our arguments, so we don't want to overproduce our bread or underproduce our bread. Number of breads is equal to which is we are producing the same number of breads which is equal. And we want to transport. Okay, now you can relate that it is the same transport problem. Right? So basically, and you want to optimize the cost, transportation cost. Okay? Well, I mean that is a headache, right, for you to optimize such thing. And so you give it to someone else who take care of your transportation problem. So he proposes the following. I will maybe erase this one. He proposes the following. Suppose this is a bakery located at a position X, and it was transporting bread to a cafe located at say Y. Okay? So what he proposes is that so he will buy the bread at a price psi x, okay, and he will sell it to the bread, sell it to the cafe located at Y at a price psi y. Okay? So he will just buy bread from places and sell it to the same some other place. Okay? And so his profit is basically psi y minus psi x. So this is his total profit. So his total profit. So what he proposes that see you are already somehow expending about CX amount of money to transport this bread, right? And he proposes that okay, my profit won't cross your transportation cost. And this is very lucrative, right? I mean, of course, it preserves your interest. His profit won't go much higher, right? So, of course, I mean, you give all his transportation, your transportation to him, and so basically he so this is his constraint. Okay, so he will buy at a price psi x and sell it at a price cy.
It's a losing business, right? It's the other way.
No.
You don't want to lose money because cost must be smaller.
No, this is losing for. I mean, it seems like it is losing for him.
Yes, if I want to transport, I must not be losing. Otherwise, why would I do business?
Correct.
Yeah.
But you see here, the way of transportation, that is very detailed, right? So I don't know. So my way of transportation
Yes.
may be different than yours, and somehow you can optimize your transport. Maybe I mean what he is proposing that I mean he has a better transportation plan. I mean not in terms of what we discussed, but perhaps some other way. Yeah.
We can put a lower bound 0 so that like some profit is there.
So that I don't want to put, and that will come later. I mean, of course, I mean this is so basically you can say that well, I put psi equals to 0 and psi x equals to 0 and phi y equals to cxy. I mean, so basically, I will not give you money and take your and I will sell it to some other place. So that is in general not possible, right? So we will see in the proof that actually it's so at a I mean, it stabilizes somehow. I'll come to that. So basically, this is your constraint. Okay? And so the total selling price is this one, right? And total buying price is so that it is his total profit. So this is the total profit subject to the constraint this one, right? And of course, he would want to maximize his total profit. This is called Kantorovich dual profit. Apparently, I mean, of course, as you mentioned, it seems like you are losing. right?
No, it's okay, because you're already making profit. You just want, if you have spent $10, you want to make sure that you don't want to profit more than $10.
Yeah,
That's okay.
yeah, exactly. Right? Yeah. So yeah, from this, so if you
Yeah, he's not losing money.
right. So so one inequality is obvious, right? If is always delta equals to k. So this is obvious, right? From it. And what Kantorovich proved is that this is actually equal. And so how this dual problem, solves the Monge problem. Okay, so let me come to this, and I will explain in a moment, and that you will also see in this argument why I don't want to talk about this one. Okay, I only want to stick on this cost. All right, so so for the moment, I don't know. This is what we are maximizing. Right? So I don't know whether it can be attained, whether you can achieve that. So this is just a supremum, right? So for the sake of the argument, assume that psi naught and phi naught. So this is a maximizing. Okay? Then from this duality, see phi naught d mu minus d mu equals to d phi. Okay, so I'm not writing x, y, so it is understood, right? P variable is always y, c is always x, and this small c is xy. Okay? Now, if
So here supreme is our all convex pairs, right? Phi and psi.
the technical assumption is say we are integrating. So first, this is the constant, and for the we will assume that these are all integrable. So this is where I want to maximize. Of course, depending on the measures, you will have more regularity. But for the moment, I just want to integrate. All right. Okay. So so this is the Kantorovich duality, and so here I want let us use, so these are functions of y, right? So let us use the marginal conditions. So I can just replace this by d phi and integrate. Here is also I can replace this by psi x and integrate d phi, and let us take it to the other side, and it is equals to 0, and let us just combine everything together. Psi 0, phi, right? So this is what we get. This quantity is 0, right? If psi naught is if this one is a maximizer in dp, and if this phi is a minimizer in k. Okay, so if phi is this is a maximizer and phi is optimal in k. This identity must hold, right? And also we have that this is always greater or equals to 0 from the constant. Okay, so this identity should vanish. Sorry, this is 5, this is phi naught minus cx1. This will vanish for phi naught to stay with x1. Right, so this is a good identity. Okay. All right. So for the moment, assume that this is your the cost is given by, say, let us say mod x minus y power p mod x minus y. Assume this is power p, which I will write h of mod x minus y. Now we have certain identity. Okay, so just for the moment, just differentiate with respect to the variable x. Okay, so I don't know whether we can do that. Okay, so just formally differentiate this one with respect to x. Then from here, I will get minus gradient of psi naught x. Of course, I don't know whether psi or not is actually differentiable or not. This one is smooth. Okay, so I have gradient h of mod x minus 1. Now here is the strict convexity comes into the play. Okay, so if H is strictly convex, then gradient is invertible. Okay? So this is x minus y is basically equals to gradient H inverse of minus gradient of psi naught, and I'm taking it radial. So from there you get, you see y, so y is equals to x plus gradient H inverse of gradient psi. Okay, so basically everything formal. So I didn't index. Yeah, no, so this is minus, so this is minus, it will come to the other side, it is radial, so that's why. So yeah, so basically, and here I use that it is strictly convex, okay, power p. Okay. See, gradient is invertible, and see for yeah. So what we get is that for each x, the where you are transporting, right? X, the y is given by a map, right? And this is what we mentioned here, that if the support is concentrated on a graph, then perhaps then it is possible to solve one problem. Okay, but here of course the argument what we did formally is we have to make it precise, okay? And I will do it in the I'll start doing it in the next class. Okay, so yeah. Right. Yeah. So I wanted to. I forgot what I wanted to mention. Yeah. So you see, the same the same argument cannot work for for distance cost run. Okay. So if you differentiate the formally, then what you get from this identity. So if Cxy what x minus y, then yeah, just get minus gradient of psi naught x is equals to x minus y by mod x minus y. And so basically, so this identity, I mean, y is the point where you are transporting the mass, right? So this is just the direction. So this is your x, and this is where you want to transport. So the direction is determined from this identity. This is given, so only the direction is determined, but you don't know how far, where to stop. So you don't know how far you have to go, like how far you have to transport. Of course, direction is given by this, but you don't know how far, and that is a major difficulty. And this is what I will not talk about, but still it is a beautiful. I just mentioned the results. Okay, so this is the original Monge problem as I mentioned. Okay, so the first, so because I don't want to talk about, I will not talk about this. I will just give you some references. Okay, so the first one, the reference, the first existence theorems came due to Sudhakar around 1977. So, but his proof, I mean, it is almost a 200-page long paper, and he used something called measure decomposition. Okay, so I'm not even brave enough to look at it, but anyway, so he first derived this result, but there was a gap which was found much later. Okay? But this actually works for dimension n equals to 2. So basically, the difficulty in his proof was that, I mean, see, these are the directions, okay? So for each point, so it gives you the direction. Okay? From the picture, you can see that at least, I mean, the main point is that these are called, I mean, transport rays, and they actually don't intersect. So as soon as they don't intersect, they have some sort of resistance bound, which is obvious for dimension 2, but higher dimension is not also. So yeah, so the point is that as soon as you have a ray, you restrict it to this ray and solve a one-dimensional problem. Okay? And for that to restrict and to get a absolute constant measure, you need Lipschitz bound, which is not here. Anyway, so the first actually complete proof advanced generals. Around 1999, so they used PD technique to solve this problem. Again, I mean, it's a long paper, and I will not also discuss in this symposium. And after that, I mean, almost simultaneously, paper of Caffarelli, Hilbert and Hacker, and Tudinger Wang and Ambrosio, almost simultaneously, they came up with the solution of the merge problem. So for different norms, so their argument was almost similar, but this was mostly concentrated in the direction of Euclidean norm, while Caffarelli, Hilbert, and Hacker, they considered for any strictly convex norm. Okay, and Ambrosio also concentrated on Euclidean norm. Okay, and later around 2001, again, I mean, these proofs are quite complicated. I mean, if you look at the article, restricting offset and using proving Lipschitz bound and change of variable and then finding a map is not always very technical. But around 2001, there are some papers, champion. So they actually came up with much simpler argument. Again, which I will not talk about in this symposium. But, their results also covers norms which are not even strictly bound. Okay, so, but yeah, I will from tomorrow onwards, I will forget about this thing, and I will concentrate only on the result of strictly convex cost and yeah.